I really want to start with a turning point in Galileo's life, the publication of Sidereus Nuncius, his telescopic discoveries in 1610. This quickly turned into an appointment as court mathematician and court philosopher to the Tuscan Grand Duke, and positions that he held for life. These two titles are actually rather incongruous. Mathematics at the time was a fairly unimportant and obscure part of philosophy, while philosophy was the theory of everything. And in insisting on this title, court philosopher, Galileo was, in a way, asking for more than he was entitled to. But I think by the end of his life, he actually had become a philosopher, and in fact had brought these two titles into a kind of harmony, that is, a new philosophy in which mathematics was much more central. And that's a kind of outline of my talk, the evolution that I promised in the title. Well, meanwhile, back in 1610, real philosophers, meaning people who had university degrees in philosophy and who knew their Aristotle, must have been outraged at this upstart who suddenly usurped the title philosopher for himself. And Galileo was attacked immediately on arriving in Florence on several fronts, the Copernican controversy being just one of them and the most successful from his antagonist's point of view. And there were attacks and rebuttals, and Galileo was now famous, so people kept his letters, and the court kept meticulous records. And in short, the documentation after 1610, after this book, is rich. And Galileo biographies are pretty much founded on that material. Meanwhile, before 1610, the record is a lot skimpier. Galileo was rather obscure. And so we have the paradox of one of the best documented personalities in all history remaining a bit of a mystery in many ways, because we can't exactly see how he developed. By 1610, he was closer to 50 than 40. So in some ways, he was a fully formed person. Now, I have, as I've already hinted, I'm interested in Galileo's mathematics and his attitude to mathematics, which in some ways I think is more important than the actual content of his mathematics. And so I've used that question, what was Galileo's mathematics, as a way to look back before 1610, because actually quite a lot of what we have is rather mathematical, the kind of thing that many biographers don't pay much attention to, but there is a lot of it. And just as an example of something that you might notice, it's very clear from the early work that Galileo revered Archimedes and even proved theorems in the Archimedean style. That is, he emulated Archimedes to the best of his ability. Now, by the end of his life, he was still saying the same thing about Archimedes to his neighbor, Niccolo Gherardini, who left biographical notes. He praised Archimedes to the skies. Nonetheless, his mathematical work by that time, in his last book, Two New Sciences, his most mature and most influential book, no one could accuse that book of Archimedean elegance. He had, while keeping the ideal of Archimedes in his mind, he had loosened up considerably the kind of mathematics that he did. To me, this is two things. That first of all, Galileo had excellent mathematical taste. Not everyone in his time responded to Archimedes like this. Nowadays, I think we would say that was good taste. But he also had good sense. That is, he was willing to relax a little bit in the service of other projects. So that's just an example of how you can sort of see Galileo's mathematics and his mathematical thought and predilections evolving. Let's see. There. Well, I just put this in to remind myself to say that Galileo's mathematics does not look like this. This is a page from Copernicus in English translation, and shows how Copernicus used ancient data to parameterize a planetary orbit. Galileo seems to have had no interest in this problem. I can't see that he ever spent time on it. And he may never even have read this sort of thing in great detail. Kepler's mathematics looks like this. But Galileo's mathematics does not. It just wasn't his style.
Of the orbital parameters of Kepler.
Yes, that's right. Kepler did just this sort of thing. This is using, this is really amazing. It's using data from Ptolemy from like 2,000 years earlier. Especially good moments. Maybe there was a close approach to a star or something like that, so where you could really fix where Mars appeared to be. And then from moments like that, getting the parameters. Galileo never did that. That's my point about this. There. This was much more his style. It's a view of Galileo's Dantes Inferno, as imagined by Sandro Botticelli, end of the 15th century. And I'm alluding here to something that Professor Mignone also mentioned, that there is a little bit of Dante in Galileo's career. And it comes, oddly, when he was 24 years old and an impoverished university dropout. For some reason, never, I think, completely clarified, the prestigious Florentine Academy invited him to give 2 lectures on Dante's Inferno. I was amazed when I heard this, because it's not mentioned in most biographies even, although it's maybe the best documented event in his early life. And then I was even more amazed to hear that we have the text. We can see word for word what he said. So why don't people talk about it? Maybe because it's so odd and maybe seems unimportant or even a little bit embarrassing. I just couldn't stop thinking about it. The lectures basically put numbers on this model. How deep were the circles? You can see the circles where the sinners are punished. And if you look closely, I wonder if I have a mouse here. Oops, oh, sorry. Back. You can see Virgil and Dante coming in at the top there. Anyway, making this as concrete and precise and numerical as possible, using evidence in the poem, doesn't seem as if it would be much of a lecture, but these were very popular lectures apparently. And they were in a tradition, that is, this was not original with Galileo by any means. The tradition goes back to the time of Botticelli, late 15th century. It was a kind of glorification of Florence and a reclaiming of Dante for Florence in a sumptuous new edition with lots of commentary at the beginning, including this sort of thing, which started way back then. I'm just trying to say everything you could say about the wonderful Divina Commedia. And also other glorious Florentines were part of these books. The beginning of the book would be little biographies of all the other great Florentines, and later editions had even more of them. So it was all in a very patriotic program. Galileo was talking about this still, and in many ways repeating what had been said before, because some dastardly non-Florentine had suggested that the Florentine model, which is here, would cave in, that it wouldn't, that this was impossible, that this was ridiculous. Now, Galileo, I think, although it appears fairly obscurely near the end of the second lecture, this may have been what it was all about. It suddenly occurs to me. And Galileo dismisses this suggestion that the roof, do you see the roof where there's the surface of the earth and the grass above. It's at the very top of the slide, of course. And the dome over the roof is not very thick. That was the problem, perhaps. So Galileo argues that that's not a problem. We know domes like this. this, that are geometrically similar to that one, and they don't fall in. Like, take Brunelleschi's dome, which even looks oddly reminiscent of the Inferno with its circles and depiction of the Last Judgment and so on. Anyway, everybody knows that is stable. So, case closed as far as the Inferno lectures went. I think rather soon after this, Galileo noticed that there was a problem. And the problem had to do with scaling up a dome of human size like this to something the size of the Earth. Because, and this is a fundamental physical insight too, when you scale things up, different attributes may scale differently. Like weight scales like volume, which scales like the cube of the scale factor, because volume is length times width times height. But strength may just scale as some lesser power, like the square. Maybe it's just the cross-sectional area of the dome. And when you look at it this way, it becomes obvious that when you scale things up, they get heavier faster than they get stronger. So in effect, they become weaker. And when you scale by 100 miles to 1 bracha, which is like, I haven't even worked this out recently, but anyway, thousands and tens of thousands and hundreds of thousands, the structure becomes weaker by that factor. And so it would most certainly cave in. This is, as I say, an incident from Galileo's early life. He returns to it at the end of his life in Two New Sciences, that last book, and makes this argument that I just made rather quickly about how different attributes scale differently. Makes that, but not in the context of the Inferno. He chooses other things, like animals. Large animals are basically scaled up versions of small animals, aren't they? So this is a problem for them. They're too heavy for their strength, unless you do something else, like make the bones thicker. So that's what this very successful drawing is meant to show. Large animals would have to have rather clunky bones in order to hold themselves up and not break under their own weight. Well, this seems to me a very interesting and wonderful connection between Galileo's early career and his final achievements. The thread of, well, I mean, what's happened here? First of all, he's discovered something fundamentally interesting, something that you can see in chapter 1 of every introductory physics book, the idea of scaling and the idea that things don't scale, that not all things scale the same way. It's the one of the bases of nanotechnology, for example. When you make things really, really small, they're not just miniature. They may even have different properties just through being small. So this is quite an important thing. And not as silly as it looked when it was just the Inferno. Another thing, and this is so kind of mind-boggling that I don't know when he realized it, but mathematics in this example has taken a leap from just numbers in some specific instance, like describing very precisely the Inferno. Suddenly, it's talking about something of much wider applicability and much greater generality. So this sudden expansion in what mathematics has to say must have been so startling to him that, as I say, I'm not sure he even realized it at first. Although by the time he wrote Two New Sciences, he certainly did, because he was by this time applying it very fluidly to other things. He never had to mention the original one, which would still have been an embarrassment, I think, to recall. And as I've said somewhere, by that time, there may have been no one left alive who had even heard those lectures, so he just kept it quiet. And they were only discovered in the 19th century. And that is, he never told anybody about them, and no one knew about them until they were published in France finally in 1855. And it was briefly thought that maybe they weren't even genuine. But then someone pointed out that it was Galileo's own hand. He had written this out in a very distinctive hand, so no no question. And as they say, thoroughly documented incident from his early life that's largely ignored.
Where were they discovered? You know?
Where? No, I don't. But since they were published in France, let's see. A lot of Galileo materials were brought to France in Napoleon's time. And most of it was returned. Like the documents of his trial were briefly in France. These should have been in the records of the Florentine Academy, so I don't see why those would have gone to France. So I did look. I was trying to think, how were they discovered then? So I went as far as finding out who published them, but more than that I don't know. And I got this from Antonio Favaro's great collected works of Galileo in 20 volumes. This is the Inferno lectures are in volume 9, and the introduction to the Inferno lectures tells us a little bit, but not the details of how they were discovered, and I would like to know. Well, so that's again there's a sort of evolution of mathematical thought there from the very specific to a kind of stunning generality. That is, the notion of scaling in modern physics is really central. Like there was Dijen won the Nobel Prize basically for this some 30 years ago for use of scaling arguments in liquid crystal theory. So this has not gone away at all. It's a very profound insight. But just one insight, and its general importance is maybe not so clear. Well, this had become a sort of method for me. Look at Galileo's mathematical thought, and even beyond what he said himself, I thought, look at what he must have known. Like, we know his education was in the arts, and so he would have known perspective theory. That's what's being shown here, how to draw things in perspective, how do proportions change with distance, and how do we represent that on a plane, and so on. It's not just that he must have known that. We have actual testimony that he did. He was considered an expert in perspective theory. Or music theory. His father would have known this book very well, even though it's a little bit antique by Galileo's time, because his father was a music theorist with access to anything he wanted, basically, through connections at the Medici court. And so Galileo knew all about music theory, too. And a good deal of my book that was so kindly mentioned is just looking at the arts and the mathematics of the arts, and therefore what mathematics looked like to him. It didn't look like astronomy. That's worth saying. He was getting his mathematics from places like this. The notion of proportionality runs through those artistic mathematical theories, so that it gradually dawned on me that that's a commonality. I only thought of that because I noticed that at the end of his life, Galileo was still very concerned with the notion of proportionality. So that's something to keep in mind. And if you look, so at the end of his life, two new sciences again, so jumping ahead 50 years and more. Here's maybe his one of his greatest results. Since I don't dare touch that thing, I'll just gesture here. What's being portrayed here is how an object that's dropped gains speed as it falls. And it's being portrayed in this very geometrical way. Time is represented by the line AB. So as you go down from A to B, you're going later and later in time. And speed is being portrayed by the horizontal lines that go as far as this diagonal. Forget about that rectangle. That's just a distraction. And you probably didn't even notice that line. Don't pay any attention to that line. Just look at this triangle. That's showing how speed picks up with time. And in particular, speed increases proportional to time. And this is just we would just draw that as the graph of speed versus time. And this may even be the first graph of such a relationship. I don't know. If someone wanted to make the case that Galileo invented the graph, I think this would be Exhibit A, but I'm not making that case. I don't know. But it's certainly an early form of that. It was very common to talk about proportionality in terms of line segments. You would draw two lines in the right proportion, and you say, this is what I mean by that proportion. But this is more inventive than that, because you have lots of lines, and then all the segments that you can get out of this line, and they're arranged one perpendicular to the other. That was not the way it was usually done. So very inventive. Talking about proportionality, I would like to say that, that this goes back to the arts and proportionality theories in the arts, because that must have been in Galileo's mind from his early days. But I don't think you can really make that case. This just doesn't look like that. You might as well argue the opposite, that he just dropped the arts as he got interested in the sciences, and then he did this. And they had nothing to do with each other. I think you could make that argument just as easily. And this, for me, was a great disappointment as I was trying to finish my book. I had gone into this study of the arts and what that must have meant for Galileo, thinking, maybe naively, that, that if I just knew all about that, then I could see what happened. But I had gone about as far as I could with the early life, and I just couldn't see how the later life came out of that. There seemed like a big hole. And then, to my astonishment, really almost by accident, I ran into this. This is an oration in praise of mathematics by someone named Niccolo Aggiunti, given in 1626. And it's exactly what I thought, on theoretical grounds, ought to exist. He says that the world is all mathematical, not just the heavens, but the world below, mathematical. And the arts show us lots of examples. And this is basically the new idea of what mathematics should be. It should be telling us about the world around us. I was so happy to see this, because it seemed to confirm what I had hoped. But it wasn't a Galileo, it was this Niccolo Aggiunti. And so I briefly thought, maybe there is no Niccolo Aggiunti. Maybe it's a pseudonym for Galileo. But that couldn't last, because Niccolo Aggiunti is actually quite well known as a disciple and friend of Galileo's, although he's not nearly so well known as he should be. In fact, most of the rest of my talk will be about Aggiunti. I think he's that important. So who was Niccolo Aggiunti? He was the age of Galileo's son, and he became really a second son to Galileo. They were that close. He graduated from Pisa in philosophy, 2 degrees actually, philosophy and canon law, in 1621. Immediately joined the Medici court because he had the reputation as a great debater and a great intellect and a very feisty young person. And he must have met Galileo immediately. And by 1624, when we have the first letter after Galileo went to Rome, and they just couldn't stay apart, apparently. He wrote letters. And this letter is so affectionate. You can tell he's just like one of the family. He mentions other family members that he's been talking to and so on. So Aggiunti and Galileo were immediately close. And he was a trained philosopher, as I said. Galileo appointed him professor of mathematics in 1626, although he was not trained in mathematics especially. I mean, his degree was in philosophy. And that was the occasion of this oration in praise of mathematics. So I thought, so here's this philosopher, mathematician, friend of Galileo, witness to the early scientific revolution, when I think what the scientific revolution was is exactly a revolution in the philosophy of mathematics. This was just too good to be true. And he left 2 volumes of manuscripts that have never been studied. Isn't that unbelievable? So 2 years ago, I was in Florence. I shouldn't say never. They've been looked at, but I wouldn't call it study. So 2 years ago, I was in Florence looking at Gal 128 and Gal 129 in the Galilean collection. The Gal 128 is scientific papers, and Gal 129 is philosophical papers. That's what you can read in quick descriptions. And I was most interested in the philosophical papers, because what was, how are they thinking about it? But this was a very forbidding book, I quickly saw. So I went to Gal 128. And here's something I saw in Gal 128. It's the beginning of what turns out to be a coherent treatise on elasticity theory when there wasn't any mathematical physics of any sort. This just astonished me. What's drawn here, well, he's thinking about how strings stretch. And this is in response, apparently, to a question from Galileo asking whether longer strings break more easily than shorter strings. It's kind of an echo of the old scaling problem. When you scale a string up, does it get weaker? Possibly that was what Galileo was thinking. Anyway, so Aggiunti has this, he imagines a sort of microscopic model of what's going on when you stretch a string. And these are little cylinders, airtight cylinders with pistons in them. So you can pull them and stretch them, but then they'll retract if you let go. This apparently was the stretchiest thing in his experience that he could use. They seem not to have had springs. Nowadays we would say springs. But he has these cylinders that he calls sifunculi. And here is the unstretched string. And then when you stretch it, what happens? Each of them stretches the same amount. They share the stretch. That's the idea that he's motivating with this microscopic model. And then he immediately geometrizes it. So here are two strings, a short one and a long one. And here are the same two strings stretched. And he says they're strained the same, to use modern language, because this is what physicists would call dimensionless strain. So he says that if you take any two parts that are equal before the stretch, and then they're equal also after the stretch, then they're uniformly strained, because that means all the little sifunculi have done the same thing. Or what turns out to be equivalent, whatever proportion they had before, they have the same proportion afterwards, which means that when two strings are equally strained, the longer one stretches more, which could be confusing, but true. So he invents the idea of dimensionless strain by thinking about it this way. And then he also invents the idea of stress. Here are two strings, a thick one and a thin one, and they're equally strained. How does that happen? Well, you have more weight on this one than on this one, because what counts is not the weight, but the weight divided by the area. That's exactly stress. So equal stress, equal strain. So he's basically invented elasticity theory. I thought that was impressive. And with that, I thought I'd understood the most important part of Gal 128, although that's only, well, no, there are other really interesting things in Gal 128. But I felt confident after this to go back to Gal 129, that philosophical volume, because that, as I said, was what I thought was should be most intriguing. And I was hoping to see, a witness at the changing of mathematics into something new. Well, that's not what Gal 129 is at all. It looks like a kind of theological treatise. It's in an almost medieval style. It argues in syllogisms and references St. Thomas Aquinas. And Antonio Favaro, the great editor of all the Galileo works, suggested that it wasn't even by Aggiunti for sort of obvious reasons. It looks as if it could have been 200 years old by then. Favaro points out that it's not in Aggiunti's hand and suggests that it was maybe just scooped up with Aggiunti's papers at his unexpected early death and found its way into Gal 129. And that's maybe sufficient reason why no one has spent any time on it. And I really mean it. I can't think of anyone who's ever looked at it. But it occurred to me that this could be Aggiunti's doctoral thesis in philosophy, because he was coming out of a very conservative philosophy department, and and why else would it be in his house? Such a strange book, unless it was his. It's true that it's not in his hand, but it's not in anybody's hand. It's been copied over, just a couple of notebooks at a time, as if the job of copying had been farmed out to volunteers, maybe university students, to do just one or two notebooks. The size of each section is that of an octavo notebook, and that's what Aggiunti used in Gal 128, because some of those notebooks are still bound in Gal 128. So the handwriting evidence didn't seem to me enough. And so this is obviously speculation, but if this really is Aggiunti talking, if it really is his philosophy thesis, then it tells us what Aggiunti was like when Galileo met him. And he was, as it turns out, looking at questions that would have interested Galileo. And this might explain, would explain their immediate friendship. After all, he was a brash young Aristotelian philosopher. He should have been an antagonist of Galileo. Those were just the people that Galileo had the most trouble with, but not with Aggiunti. They were fast friends very, very quickly. What Aggiunti is doing in this 300-page tome is apparently synthesizing Aristotle's De Anima, on the soul, with Aristotle's logic in the Catholic theological tradition. And here's question 1. If I can just get there. Questio prima. Whether logic is in the nature of things and is necessary for the acquisition of other knowledge. It develops that he's thinking about how we know things. Where does our knowledge come from? Well, we get sensory information, but then we have to do something with it. Is logic necessary for that? So that's one of the big questions put right at the beginning. His idea is that there are 2 kinds of logic. I think this is maybe original with him, although I would be delighted to know more. He distinguishes artificial logic and natural logic. Natural logic is what is kind of effortless, I think. The senses just do it. The way in the optic nerve, a certain amount of computation takes place. Obviously, he doesn't mean that, but we too think that happens. There's a kind of natural logic that before we are even conscious of things, it just happens. And then there's our conscious working on things. That's artificial logic. He argues that the angels don't need artificial logic because their natural logic is so powerful that they apprehend things completely and immediately. And maybe Adam had that kind of natural logic. He raises the question without saying. But we don't. We need artificial logic. So that's in the thesis. Oh, and by the way, what kind of other knowledge is he talking about? There are 2 two last questions. This is one of them, but they're both rather like this. It's about the immortality of the rational soul. So he's talking, and this would be a typical question in a philosophy department, apparently. So he's talking about that kind of knowledge. Can we know that we're immortal? But it's all argued at such a plane of abstraction that it could apply to any kind of knowledge. And Galileo had just been dealing with such questions in the context of the Copernican controversy, where he argued that we read the book of nature as the work of God. God talks to us not just through Scripture, but through his works. But how do we read the book of nature? That's what Aggiunti was theorizing. How do we read the book of nature? So they might have had something to talk about. And they were both famous debaters and loved arguing. And they would have differed precisely on the question of logic and mathematics. Galileo would have said it's not Aristotelian logic, because that's what Aggiunti meant by logic. It's not Aristotelian logic. It's mathematics. So they would have gone round about this, and that would have been a lot of fun for them, and I think would completely explain their friendship, and would explain how Aggiunti came to be appointed professor of mathematics when he wasn't really a mathematician. It's because they had this new view of mathematics now. Aggiunti was won over, that's very clear. And therefore, mathematics assumed a philosophical place that it had never had before. It took the place of artificial logic, which is the basis for everything we know. So you find in the oration, for example, Aggiunti says, everything we know is through mathematics, whether you like it or not, he says. This truth may be may be difficult, but I assure you. So that's my reconstruction of what happened when Giunti met Galileo, and they argued, and suddenly mathematics took on more philosophical heft than it had ever had before, partly as a descendant of medieval theological notions, which it replaced in this new philosophy. That's my suggestion. So here's how Galileo talks about mathematics in maybe his most famous passage ever. It's from a book published in 1623, 2 years after he met Giunti. He doesn't say this before. This is, I think, the first place I know where he talks about mathematics with such universality. I'll just read it out since it's so beautiful. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth. Incidentally, in Il Saggiatore, he says this to Sarsi, his antagonist in the book, but he's talking about arguments that Sarsi has made that are mathematical. It sounds as if he's talking to someone who doesn't know about mathematics, but he's not. So it's rather, I mean, it's not clear why this is there, except that this was very much on his mind, I think.
This is the book that was first published anonymously, right?
No, Il Saggiatore was, no, that was much earlier. There is such a one, yes.
It's interesting that he equates the language of mathematics with geometry rather than...
Yes, the characters are, right. He was never an algebraist. Geometry was for him mathematics, yeah.
Today, I mean, if I were completing, if you wrote that sentence and left a blank there...
Yeah, its characters are X and Y and Z.
Right.
No, he doesn't say that.
Symbols.
Yeah, right. Yeah, there's so much to notice. So this is evidence. I have two little excerpts pointing out that the appointment of Giunti was really the establishing of a counter chair in philosophy. That is, the chair in mathematics wasn't just mathematics anymore. That they envisioned a new philosophy that had mathematical content. So this is in a memorial oration 2 years after Giunti's death. The dean describes how Giunti, after the lectures, would then spend time with his students going over philosophical questions. Not usually what a teacher of mathematics would be doing. And Giunti himself says this. This is in a letter just a year after he took the post, a letter to Galileo in which he makes it pretty explicit that it's counter to Aristotle. After the usual lesson in geometry, I've started to propound and resolve some physical problem, but that means some philosophical problem, I guess, since quickly we run into Aristotle. I mean, as the theory of everything, Aristotle talked about physical problems, of course. Well, okay, I think that's really all I had to say. Maybe I'll just finish by saying that thinking about Galileo's mathematics and his mathematical style seems to me to be a very fruitful way to look at him. There's lots of material, and it typically isn't much talked about because the people who usually write biographies kind of skip over the mathematics. So there's interdisciplinarity for you. I didn't talk very long, did I? So I think we have a lot of time for questions. Yeah, Nick.
I have a question about atomism. Does atomism feature at all? I mean, this is the crucial moment around the Saggiatore with issues of scaling. Excuse me. There's you talked about scaling down as well as scaling up.
Right.
And I know I was very surprised to see in the Gal 128 the use of vacuums as vacuum chambers. I mean, that's a really provocative topic. What is a vacuum at the
Yeah. It might just be rarefied if there was a little air in there, but...
But is there an idea that there's a physical limit to mathematization?
Well, atom, meaning not cuttable, sort of suggests, I guess, a limit to how small you can go. But in two new sciences, Galileo sort of packs all his old material into two new sciences, and he does talk about that, as I'm sure you know, whether maybe the reluctance to form little vacua is what holds matter together, whether the cohesive forces that make solid solid is really the vacuum. And he even argues against that, I believe, in saying this. We would say this is an unrelated phenomenon. But anyway, pumps, water pumps and air pumps were just being devised, the pumps that could really do something, I guess. And if you try to pump a column of water up, you can't get higher than 10 meters, about 30 feet. And then it's, well, I was going to say it breaks. That's what Galileo said. I'm not so sure. I mean, it cavitates, really. Gas in the water comes out and forms a bubble. But anyway, I think he argued on this basis that the forces, the vacuum forces between particles was not all that strong. No stronger than you could generate yourself with a pump. And that couldn't be what makes solids solids, because solids are so strong, some of them. So he's very, very fascinated with the microscopic, yes, in various ways. And there are ingenious arguments about infinity, which people look at in retrospect and say, "Wow, that's Georg Cantor's argument." The book is a little bit undisciplined. Some of it is just, he takes up things and leaves them. But so the microscopic is certainly a big topic with him, and I can't think that I've noticed anything very good there. But I bet there is something there. I mean, I haven't drawn any kind of surprise out of that. Yeah.
Did you come across any references to Galileo as an astrologer?
He did make horoscopes for his children, and he certainly knew how to do it. That's what he was teaching, pretty much, I think. I mean, a professor of mathematics, that's what he was at Padua for 18 years, was mainly there so that medical students in particular could learn to cast horoscopes correctly. So he knew how to do it. And this, people have talked about, I sense a little diffidence about this topic, because people don't want Galileo to be an astrologer. And he certainly didn't have the confidence in astrology that Kepler did. I can't think of any place where he sounded confident. And there's an interesting letter, I've forgotten by whom, from his days in Siena after the trial in late 1633, when he was there as a guest of the Archbishop and trying to recover from the whole trauma of the trial. The topic of astrology came up, and he was very disparaging on that occasion. But that was pretty late in his life. So I don't know if that evolved.
I've seen that letter, and I tried to at one point to write a paper just for a course in the history of astronomy that I was taking. I actually did an early translation of that letter. But I tried to make the case that his interest in astrology led him to want to observe the heavens, and sort of led him to I won't say look for a basis for astrology, but to basically to use his senses to more deeply understand the natural world around him. And in a sense, I mean, I was an astronomy student at the time. In a sense, I was trying to there's always this chasm between astronomy and astrology, and
people don't want to go there.
Astrology, but I tried to make the argument that at least astrology initially was based on observation. It's no longer based on observation. In fact, it uses old tables describing the movements of celestial bodies that aren't even accurate anymore, but I tried to at least give astrology a little bit of credit for at least providing the foundation for Galileo to want to observe the heavens in the first place.
I think that's a better description of Kepler than it is of Galileo.
Yeah.
I can't think of anything that really affirms that in the case of Galileo. Where Kepler is very explicit.
I wasn't really able to make that argument.
Yeah. I was going to ask you if I seem to have represented the letter correctly, where he finally, at age 70 roughly.
And basically, at least he was re-examining it, but still in my opinion, he still owed something to,
Galileo was remarkably uninterested in astronomy, actually. In 1607, this was just before he turned the telescope on the moon. In 1607, he wrote a kind of defense against one of his students who had plagiarized one of his books, he said. And this student, unfortunately, had observed the nova of 1604 before Galileo had. In fact, he was the first one in Padua to do it. So he was kind of, I guess, famous as an astronomer. And Galileo says, in leading up to his main argument, which is defending himself, all credit to the first observer, but it may well be asked whether someone with an ambition to excel in the mathematical sciences should spend every night of his life looking over the roof of his house on the chance that some new object might appear and someone else get the glory of that discovery. Of course, 3 years later, he was doing that himself.